why is it that XRF can only detect elements and not compounds? Well, as we said in the last video, if we imagine that the atoms look something like this is the nucleus, this is not to scale, nucleus. This is the first shell, second, third. Compounds really happen because what differentiates a compound, by the way, is that there's essentially an exchange or interaction of the valence electrons. And for these larger atomic numbers, where they have at least 4 electron shells, primary electron shells, the valence electrons are these outer electrons out in here, and X-ray fluorescence happens in these lower core electron shells. So these are really largely unaffected by what's happening out here. In addition to that, what differentiates compounds from elements is not only this difference in the valence electron exchange or sharing, but also in a different crystal structure, likely. And so X-ray fluorescence can only detect these electron transitions here. They can say really nothing about crystal structure or what's happening with the valence electrons. What determines the intensity of an X-ray energy on the spectrum? Well, if we have a spectrum, I drew one on the other graph. I'll just kind of draw one quickly here. Here is intensity, which is really counts. These are essentially the number of photons with a particular energy. And here's the energy axis here, KeV. And an X-ray spectrum, energy dispersive spectrum, for example, might look like this, where you have different emissions, and those emissions have different ratios of intensities like this. Well, what that means is that there are a whole bunch more photons that have this energy than have this energy. So the intensity is really typically the number of photons that have that energy. I think a lot of you confused intensity for proportional to the amplitude of a wave, which is not incorrect, but for X-rays as a particle, typically that's what you're doing, is you're counting particles when you look in X-ray fluorescence, and you're looking at the number of particles that have a particular energy value. So in this case, this energy value, how many particles do you count that have that value? So the energy per photon, I think people got that confused with amplitude and with intensity, when really this intensity on this graph really is just the number that have that energy. So this has more that have this energy than have this energy, and that is simply due to the fact that it's more likely when you, let's say, knock an electron out of, boom, this goes out of this and leaves an empty seat here. When you knock that out of the K level, it is more likely that the replacement will happen from the next shell versus 2 shells away. And so the statistics of the replacement between these 2 competing processes, they favor this guy, which is closer. So there's just the intensity itself is determined by the probability that each one of these will happen. This is much more likely since these electrons are closer.